I think that's it for announcements. So our first speaker to kick off today is, I think this is really special for Adriana because normally for whatever reason, Adriana is bringing up the rear, right? She's that 3:30 speaker on day 4 of almost every conference. But nope, she's kicking us off today with a very important subject, which is a test that is going to check, help us check the embedment of our seal coats, our chip seals. So Dr. Adriana Vargas is an associate research professor at the National Center for Asphalt Technology, NCAT, with 18 years experience in pavement management, preservation, and rehabilitation. She has led research products funded by FHWA, NCHRP, NAPA, ISSA, and multiple state DOTs, delivering solutions that directly support pavement performance and cost effectiveness. Her background includes academic roles at the University of Costa Rica, industry experience with Nichols Consulting Engineers in California. Dr. Vargas is actively involved in professional organizations including AAPT, ISAP, TRB's Pavement Maintenance, Preservation, and Rehabilitation Committee, the Emulsion Task Force, and serves on the Board of Directors for the Southeastern Pavement Preservation Partnership. And she probably won't like this, but you know, Adriana started in the hot mix side, and they started with PG1, the preservation group, and I believe Adriana has drank the Kool-Aid on pavement preservation. She's one of us now, so come on, Adriana, let's do it. Thank you.
Well, good morning. Thank you for having me today. What I'm going to talk about today is a project that's being sponsored by NCHRP, and it's about developing a field test to check embedment for chip seals. With that said, they had to review my slides and made me put this disclaimer in here, just twice, not just here, but here and at the end. So you'll see that. You can read it later. Basically, this is an NCHRP project. We have a great research team. I'm the PI and representing NCAT for that. We are also working with the University of Arkansas and Andrew Bram and his group. And there's also a center that is part of the University of Arkansas, the Center for Advanced Spatial Technologies. And you'll see in a little bit why this is relevant, but they have a lot of really innovative things that we wanted to try. So we have a couple of people from that center helping us with this. And we also have Scott Schuler, who's really knowledgeable with anything with chip seals. So he's one of our consultants for this research team. To give you a little bit of background, well, I don't think, again, I'm preaching to the choir here. So we all know chip seals are really cost-effective ways to maintain and preserve our pavements. They're really popular with many agencies just because of all the things that you can do with them. So you can help seal that pavement surface, correct some minor cracking, things like that, and give us also a skid-resistant surface. We can see from different sources, you could expect life extension somewhere between 5 and 10 years, which is pretty significant. That depends on whether you're doing single layers or multiple layers. But all of this makes them very attractive to any agency because you can really achieve a lot with a relatively low price. One of the things with chip seals, so when you're doing a design, you'll take inputs such as the aggregate size and type, the surface condition, traffic, all of that. Use that information, and then you can calculate your application rates for the aggregate and for the binder. And with any type of design that you use, because there's different design methods, typically what you're doing is targeting a given percent of embedment of that aggregate. And that will range somewhere between 50 and 70%. the point here is that you don't want too much embedment because then you're going to start seeing bleeding. But if you don't get enough, you're going to start losing your aggregate. So you want that good balance between the two that you can have optimum performance, and that's the whole point with the design. Now, embedment in itself is just looking at how much your aggregate particles are, well, embedded into that binder, whether it's a hot applied or an emulsified asphalt binder. And that is calculated by measuring the average least dimension of the aggregate particles and how much of that is into the binder. So we know the theory behind it. And we also know that that embedment could be different at different stages during the chip seal construction process. So when you first drop those chips into your liquid, it may be around 50%. After you have initial rolling, that goes up a little bit more. And once you have more traffic in your chip seals, then you really are able to embed those particles. So it may vary at different points in time during your construction process, which also can be significant for this project. So all of that said, embedment is really a key part of our chip seals and to have chip seal success. But really, nobody's actually checking it, or they're checking it based on experience or just a visual inspection. So more commonly, an inspector will come, if anything at all, and pull out a chip and say, okay, that looks about right. And we know that that's not ideal. We would like to have a more objective way to be able to determine if you're actually achieving the rates that you're supposed to be getting, and be able to take any corrective action during construction if that's the case. So the objective for this project is to either identify, adapt, or develop a test. It has to be a rapid test that you can do during construction, that you can get your results relatively fast. And it has to be very practical also, because we want to use that for just quality assurance. For our research approach, we have 3 different phases, and we're right now on phase 3. But we've already gone through just the typical literature review. We did a survey and all of that, put all of those results into a report and sent it to NCHRP for review. Then they let us go into phase 2, which is more of our development of our work plan and another report. And right now, after we got their blessing, we are actually working on the development of the test. So for our first part, right now we don't really have much information on what that test is going to be like, but this is just an update of where we are and how we got here. We did a lit review looking at anything that exists out there that maybe could be used to do exactly this and measure our embedment. So we identified different types of methods. There's volumetric methods, there's stylus profiling, there's different laser-based devices. And then we looked more at imagery-based methods. So I'm gonna show you a little bit of each of those. So the volumetric, more commonly, it would be like a sand patch test, and I think probably most of you are familiar with that. You can see it there in the picture. You're just trying to do that circle with the sand, or actually it's glass beads, and helping you to estimate the volume, which eventually will lead to texture. There is a previous NCHRP study that has a proposed method for using this specifically to calculate your embedment, and it's very accurate. However, it's not exactly practical to be doing your sand patch testing during construction. There's other devices. We went way back and looked at things that had been around since like the 60s, 70s, whatever. So there's like a grease patch test, which is basically the same thing where you're just using grease. There's a putty impression test where you're just kind of casting the surface and looking at that. There's the outflow meter, which actually uses water and lets it just flow out of a device, and you calculate how long it takes for that water to flow, and that's an indication of texture. it didn't seem like it was going to work that well with an open texture like a chip seal, so we kind of ruled that out. But in general, these volumetric tests are very accurate and inexpensive, but they're also operator dependent and time consuming. So there are pros and cons in there. Stylus profiler, you're just basically tracing that surface, and it's also very accurate and inexpensive, but it's very limited into just measuring a small part of your surface. And then now looking at newer technology, we have laser-based devices, which could be stationary, they can be walking devices, they can be our high-speed lasers that we have mounted with our profilers, even LiDAR. So all of those fall into a now different category. They can have very high resolution. Depending on the device that you use, you could have a larger coverage area, so that is definitely a pro. And more importantly, they're very fast and repeatable. So you're taking that element of having different results depending on who's running the test. Now it's really repeatable. But now your cost goes up, and they're also sensitive to some other external variables. So now your environmental conditions and all that could play into it. But this is definitely now more on the side that we want to be, of something more practical and easier to do. And then we also looked at imagery-based methods. So you could do, there's been studies in the past where people have taken cores and then they slice them and then they take pictures and look at them, which is great because you really get the picture, but that's definitely not practical for construction. There's also close-range photogrammetry and structural light projection. So all of these are accurate. And one of the things that we found that was very attractive is that there's potential for you to actually just use your cell phone, capture the information, and get that from there. So if we can use something that everybody already has in their pockets, that will be basically our best case scenario. Now, with those come other things like, well, how do we process all that data? And if we're doing things based on images, for example, there could be additional things that affect our measurements, so like the light or any shadows or anything like that, that could be potentially a source of error. So we took all of that information and started thinking, well, these are our different options. We also wanted to get some perspective from state DOTs and what they're doing, what they're not doing, what they think they could be doing. So we started reviewing just specifications from all of the different state agencies. Most agencies do have a spec for chip seals. That's pretty, I think 40 plus states have one. But only 22 agencies specifically and explicitly mention embedment, which is surprising a little bit. And most of them, they're just referring to you have to achieve proper embedment or you have to have adequate embedment without really saying what that is. So there's some awareness that this is important, but still not really built into the spec. Some agencies just refer to you got to have a certain number of roller passes to make sure that you have that proper embedment. So we looked at all of those specs. The ones that did have some mention of embedment, it's 8 different agencies. So now it's getting smaller and smaller in terms of how specific they are. But there's a few DOTs in there that do have a little bit more guidance on embedment. And you can see there, typically we're talking 50, 80% embedment or so. PennDOT actually there, they say they require Fox seal if you have less than 50%. So you can see there just a few notes. So based on that, we took those 22 agencies that actually did have a mention of embedment, even if they just said proper or whatever. And we had a targeted survey for them. So we sent them a few questions to gather additional information. So you can see there the blue is states that we contacted and they participated, then a few of them didn't respond, and then anything in white We just didn't contact them because they didn't have any mentions of embedment. We also sent the survey to some contractors, local agencies, material suppliers, and we got a good mix of responses, so I think we had representation from all sides. And there were several questions in there, but I just want to highlight this too. So one of the key questions here was, do you use any tests to determine aggregate embedment? And the vast majority don't run any tests. And for those that do, it would be just a visual inspection. So again, we're going back to, we kind of do this, but not really in a structured way. There's probably a couple that did sand patch testing or some digital analyses. And then another important question was, well, when are you checking embedment? And this was very interesting to see that there were all kinds of responses here. So it could be right after sweeping, or it could be in between roller passes, or after you just drop the chips. So that just brings us to our key takeaways here. Embedment is really a key component, but it's rarely measured. There's various tests that we could be using for this, and they're worth exploring. They really range in how difficult they are to run, how much they will cost, and all of that. But for the most part, we're relying on the relationship between texture and embedment. Now, our test that we have to develop as part of this project needs to be effective over a range of values. So we want to make sure that it's not just measuring at 70% and being accurate there. We have to be accurate at the low end and at the high end, so if you're out of spec, the test can pick that up. And we have to be able to run the test at different points during construction, again, because there may be people who run it a couple of days later, or maybe people who run it right away. More than anything, the test has to be practical, or it's just not going to go anywhere. So with all of that, we took all of those tests that we had identified and came up with a rating system based on 5 different categories. So we looked at accuracy, simplicity, cost, time, and practicality, and we put them on a 1 to 5 scale, and then listed everything and just kind of looked at the total points that they were getting. So with that, we selected the sand patch test, the laser texture scanner, or LTS, circular texture meter, and photogrammetry as our preliminary test to just kind of see how, if they show any promise, should we kind of move on with this for the actual work plan. One thing is that these methods all measure different things. So for example, your sand patch test gives you a mean texture depth. Your laser devices will give you a mean profile depth. There's different outputs from them. But the important thing here is, whatever metric that is, can you capture that relationship between your parameter and the percent embedment? And that's what we wanted to look at initially. So we started with our preliminary lab evaluation. And our first part of that, stage 1, was to build a reference sample. And we went on and bought this wooden cubes that were 10 millimeters each side. So now we have a bunch of particles that we know are all symmetrical and they're all the same. And we kind of made this fake chip seal. We know it's not really what a chip seal is supposed to look like, but we have total control of what those actual measurements are. So we embedded those to a known depth of emulsion, and we were like, well, let's run the test and see if what we know from how we made the sample matches what the test is measuring. So we compare the different methods. A second stage was, now we're going to use actual chip seal aggregate. And we selected different particle sizes so we could, again, see if that's going to be important or not. We fabricated to the design embedment rate that we would get from the AASHTO design method, or the design standard. And we determined the average least dimension based on the gradation and the flakiness index. So for our testing, we did, this is the laser texture scanner. We kind of fabricated that sample in a big tray, just split it into quarters and set the device down, let it run. What it will do is scan multiple lines, and then from that it builds a 3D surface, 3D model. One thing with this device is that you can have, I think it's somewhere between 1 and 1,000 scan lines. And obviously the more lines you run, the more resolution you put into your model, but the more time it's gonna take for it to run. So we're like, well, is that gonna make any difference? So we played a little bit with that. The top picture shows a model built based on 20 scan lines, and we got a mean profile depth of 4.72 millimeters, and we got that done in about 1.5 minutes. Then we ran 100 scan lines, and it didn't change that much. It was 4.85 millimeters now, so it's a little difference, but it's probably, in the big scheme of things, not significant. But that takes 7.5 minutes to run. So can we live with doing it a little less resolution, but faster? I think that's the balance that we're trying to achieve, and the project panel is very set on, we are willing to sacrifice a little bit of accuracy for the sake of time and practicality. We also ran the circular texture meter, so that one is also a laser device, but it goes in a circular pattern. And what I wanted to show here is that it's very repeatable. So this graph here is actually 5 different runs in the same location, and they're basically all on top of each other. So that was a big pro. The device is a little clunky and just kind of big and not as easy to handle as the LTS, but we wanted to explore that as well. Then we did photogrammetry. So this is an interesting approach. What you do with that is you take a series of different overlapping pictures, and based on certain reference points, you put that into a software, and it will build that 3D digital elevation model based on all of those overlapping points in the different pictures. So that was a good option because, again, you can use just cameras, any camera. So it could be a high expensive camera, or it can be your cell phone, and you can achieve this elevation model. So that was something that we wanted to explore. And finally, we did our sand patch testing. Now, I mentioned before that the sand patch is not really the preferred method, but it's the only one that's being kind of used right now. So we selected that, not thinking that we're gonna end up recommending to do the sand patch, but to use that as our baseline. So this is what exists right now that people could be using. What else can we do that compares to this that could replace it? So this is more for reference than anything else. But we did sand patch testing. This is all the same sample, so we did this last just to try to match some of the locations for the other scans that we got. So with all of that, for a reference sample, we found that our actual embedment rate or embedment depth is there in the orange bar. You can see how everything else that we measure, because it's different metrics, they kind of vary. So it's not a direct measurement necessarily. There has to be some sort of correlation in there. But actually, the photogrammetry method is closest to just having that direct measurement. So that is one big pro in there. Also with photogrammetry, and this is probably different than any of the other methods, it also gives you a distribution of that depth of the particles. So you could potentially use that as a percent within limits type of approach when you're measuring that. So that was interesting. I know that you can't really see that in here, but that's kind of the distribution of the particles. Then looking at our aggregate samples, so we had different sizes for the aggregate, and we're looking at that relationship between the design embedment before rolling and then whatever it is that we're measuring with those tests. So it could be MTD, MPD, or the depth from photogrammetry. But what we see here is there's always a relationship. So that's encouraging. We can see there's a trend here, and we can use that to actually build some kind of equation where you measure, put that number into that equation, and you get your embedment. So it's good to see that with all of these, there's that relationship between what the device is measuring or the method is measuring versus the design embedment. So that shows that any of these could be promising. We also look at the digital elevation model from the smartphone images. And one thing here that we need to keep in mind is that you're basically looking at the highs and lows within a given radius. And the software is trying to find that depth. But you have to tell the software what that radius has to be. So we are also looking into, well, how do we define that? You can see this, our average least dimension was 9.4 millimeters. So we ran the radius at different distances, and it is sensitive to that. So we found that running something closer to that average least dimension was going to be more effective to get better results. So our takeaways from this task is that all of the methods that we looked into are capturing that relationship between whatever parameter you're testing and embedment, which is good. Sandpatch and photogrammetry, we're showing the better correlation, although you can see there that for all of them, it was a good correlation. The LTS had a little bit more variability, but with some refinement, we could use any of these test methods for the field testing part. After we met with our project panel, we developed our testing plan. They did mention that they wanted to look more into the innovative methods, so we made a few adjustments in here, but we came up with this test matrix. So we're going to do 3 by 3 by 3 factorial design, and that means we have 3 factors at 3 levels each. So we're going to look at doing our lab portion of the study with different gradations. So we're going to have gradations A, B, and C, and this comes from the AASHTO standard. We're going to try different embedment levels again because we want to make sure that we are accurate over a big range of embedment. So we're going to try 40, 70, and 90%. And for the imagery-based methods especially, we're looking at different aggregate colors, just in case that becomes an issue. So we're looking roughly what we define as light, medium, and dark aggregates. And what we're going to do is we fabricate our samples to those known embedment levels and then test them with the different devices and see the difference between the actual and the measured and which one gives us the least error. So we're going to consider 4 different test methods. Again, we continue to look at the Sandpatch just as our reference. It's a volumetric, it's known, it's just something that's been around for a long time. But we're also looking at laser scanning, specifically with the LTS. We're gonna do also the photogrammetry method, so with the different overlapping images. And we're adding now, instead of doing the CTM, which is also a laser-based device, we're gonna do structural light projection. So with that, what you're doing is projecting a known pattern of light onto a surface, and depending on how that is distorted, the software can calculate the texture of that surface. So that's pretty interesting. And for that, we're using a handheld device, which is this one right here, that you kind of just walk around your area that you want to scan, and you just do that, and you can have a direct reading right away. So that seems interesting. We hadn't considered it before because it's not a device that like everyone has, but maybe it is worth it for agencies to start acquiring something like this. And this is where that Center for Advanced Spatial Technologies comes into play because they have all that expertise. We're also adding a field evaluation portion for this. So all of this that we're doing in the lab is obviously very controlled, and that's kind of how we want it. We want to start with the easy part and then start just making it a little bit more complex. So there is a part here where we're going to be looking at different situations in the field that maybe bring something new to the table. So we want to test in different geographic areas. We want to look at, well, things like, well, are people using wrap? Does that make any difference or not? Rubber chip seals or hot apply, does that make a difference or not? So introducing new variables and seeing how that may come into play. We're also doing a performance evaluation, so we want to make sure that the test can capture good performing chip seals and bad performing chip seals, that it can differentiate between the two. So we're gonna do some testing, select a couple of combinations of aggregate and gradation and color with one asphalt emulsion, design that to the optimum rate, and then a high and a low. Use some performance testing to look at things like aggregate loss and bleeding. So the idea here is if we built a specimen, ran it through some simulation of loading, and then we see bleeding, if we had run the embedment test at first, and we saw that it was high embedment, and then the sample's bleeding, then it's capturing that potentially there's going to be a performance issue. And the same thing with aggregate loss. So run the test, put it through some traffic simulation, see how it performs. Is the test able to tell us this is going to be a good performing chip seal or not? So with all of that, and we're in the process of making all of those specimens, and we're going to be soon testing with our first method, which will be the laser-based. And I think this is exciting. I like it. I like the job that I have because it lets me do crazy things like this. So hopefully I can bring an update at some point, but this is where we're working on, and always keeping in mind that we have to put practicality at the top of the list here when we make our recommendations. And that is all I have.
Any questions for Adriana? Okay. Two, if you don't mind.
Yeah.
Number one, when are you taking this testing? Is it just after it's being applied? Is it a month after?
Well, that's part of what we wanted to see with the with our survey. When should we be doing this? And it seems like we have to be ready to do it at any point. So if they want to run it right after finish rolling, then the test has to be able to do that.
Okay, because I would worry about acceptance testing. Are they going to use that for payment, or are we going to have to wait down the road to see
Yeah.
if it's flushing on something?
No, it has to be able to do it as quickly as possible. But we know that there are people who wait longer to check on it, so I guess it will depend on the agency. But on our side, we have to make it so that it's almost immediately as you put the chip seal down.
So how do we also deal with rutting and things like that that are going to cause different embedding depths throughout a pavement or a profile?
That will be part of the field evaluation. So with our lab testing, everything is nice and controlled, and we're like, okay, this is accurate here. And once we move to the field, those are the kind of things that we have to look into, like the existing substrate. How does that play into it? Yeah, differences over the length of the project. How many tests do we need to run? How many locations? All of that will be part of that field study.
Any other questions? All right, thank you very much.
Thank you.